Every town has one. A giant tank on stilts looming over the rooftops. Most people drive past it every day and never ask the obvious question, why is it up there? The answer is older than electricity. A water tower is a machine with no motor, no moving parts at the top. Just a tank, a pipe, and gravity. Tonight we slice one open and watch it work. Start with what your faucet needs. Water doesn't flow on its own. To climb to a second-floor shower, push through a narrow pipe, and still come out strong, it needs pressure, roughly 40 to 80 pounds pressing on every square inch. A city has to deliver that pressure to thousands of faucets at once, all day, even when half the town turns on the tap at the same moment. Pumps alone could do it. But pumps fail, and demand never holds still. Here's the trick. Lift water high, and the water itself becomes the pressure. Every foot of height adds about 0.43 pounds per square inch at the bottom. Climb 100 feet, and the column below pushes with about 43 pounds per square inch. No motor required. That's why the tank sits on legs above the tallest buildings it serves. The tower isn't storing water for fun, it's storing height. Height is pressure you can bank. Down at ground level, pumps do the hard work, quietly, on their own schedule. They pull treated water from the plant and push it up into the tank, usually at night, when the town is asleep and electricity is cheap. The pumps don't chase demand minute by minute. They just refill the bank. Run steady for a few hours, top off the tank, shut down. The tower lets the pumps live an easy life, and easy machines last decades. Slice the tower open and you'll find something surprising. Most towers have just one big pipe, the riser. Water goes up it to fill the tank, and back down the same pipe when the town drinks. No valves to switch direction, no second plumbing run. When pump pressure exceeds the tank's, water climbs. When demand pulls pressure down, the tank drains. The pipe doesn't decide anything. Pressure decides, and the pipe simply obeys whichever way it leans. Now watch a weekday morning, 6 in the morning. Showers, kettles, sprinklers, washing machines, demand triples in an hour. No pump station could spin up fast enough to match it perfectly. But the tower doesn't need to react at all. The water is already up there, already pressurized, already connected to every pipe in town. The level in the tank simply falls a few feet, and nobody's shower so much as flickers. The tower absorbs the rush like a shock absorber. Then there's the day everything goes wrong. A blackout kills the pumps, a fire breaks out, and hydrants start gulping over 1,000 gallons a minute. The tower doesn't notice the difference. Gravity doesn't need the grid. A typical tank holds around 1 million gallons, about 1 day of normal use for a small city or hours of firefighting at full flow. That's the quiet second job of every water tower. It's an emergency battery charged with water instead of electrons. So who's in charge? A level sensor in the tank, sometimes a float, more often a pressure gauge that reads the water's own weight. It reports to a small controller which watches 2 lines drawn on the tank in software, low and high. Level drops to the low line, pumps switch on. Level reaches the high line, pumps switch off. That's the whole control system. A thermostat for water, the simplest feedback loop in civil engineering, running for a century. One enemy can beat gravity, ice. In a hard winter, a still tank is a freezing tank. So operators keep the water moving, cycling the tower daily so fresh, slightly warmer water from underground mains rises up the riser and stirs the tank. Some towers add insulation or small heaters in the riser pipe, the narrowest and most vulnerable part. Even so, in February you'll sometimes see a skin of ice riding on top of the water, drifting like a tiny Arctic sea. Why the strange silhouette? A fat bulb on skinny legs. Because only the top matters. Pressure comes from the height of the water's surface, so engineers put nearly all the volume up high in a wide, shallow bowl. That way, the level barely changes as the tank drains, and your shower pressure stays steady from full to nearly empty. The legs are just there to hold the bowl in the sky. Form follows physics, right down to the spheroid. Not every place needs the stilts. A hilly city can cheat. Build a plain ground-level tank on the tallest hill, and the landscape becomes the tower. Flat prairie towns have no such luck. That's why the Midwest skyline is dotted with tanks on legs, often painted with the town's name like a badge. And skyscrapers? They're too tall for any tower, so they hide their own small tanks and booster pumps on the roof. Same trick, stacked higher. Run the whole chain one more time. The pumps lift treated water up the riser at night, banking it in the tank. Height turns that stored water into pressure, about 43 pounds per square inch per 100 feet. The single riser pipe lets the tank fill or drain as pressure shifts. The morning rush draws the level down, the tower buffers it without blinking. A level sensor flips the pumps on and off, and if the power dies, gravity keeps every faucet and every fire hydrant alive. Next time you pass that tank on the horizon, you'll know what it really is. A battery made of water, a pump's day off, a fire department's backup plan, all running on a force that never takes a day off. The simplest machines hide in plain sight. Thanks for watching The Cutaway. Subscribe and we'll slice open the next one.